the AI learning cycle. Let's visualize that same process in a slightly different way, because sometimes seeing the cycle as a flow makes it easier to understand what's actually happening. Now, let's start at the top. Input examples. This is where everything begins. The system is given data to work with, not instructions, not rules. It is just given examples. These examples could be images, text, user actions, or sensor data. At this stage, nothing intelligent is happening yet. The system is simply being exposed to the information. And now, once it has enough examples, it moves to the next step, finding patterns. And this is where the system starts to detect relationships. For example, certain words tend to follow others, certain visual shapes tend to appear together, and certain behaviors lead to certain outcomes. It's not labeling them in human terms, it's identifying statistical relationships. And this is the core of learning, recognizing structure in data. And once the patterns are identified, the system uses them to make predictions, and then it adjusts itself. And this is the adjust model step. Based on how accurate its predictions are, it tweaks its internal parameters. Think of it like calibration, small adjustments that gradually improve the performance. If it predicts incorrectly, it shifts entirely, and if it predicts correctly, it reinforces that direction. And now, after adjustment, you get better output. The system's predictions become more accurate, more consistent, and more aligned with the real patterns. And this is the visible improvement, the part users actually experience. But the process does not stop there. It loops and it repeats the cycle. When new data comes in, new patterns are found and further adjustments are made. And with each cycle, the system refines itself. And now, the important thing to notice here is this: there is no final done state. The learning is continuous and it happens as long as new data comes in. The cycle can continue, and that's what allows these systems to adapt over time, not by being reprogrammed, but by continuously learning from new information. Let's understand the differences between traditional learning and machine learning. Since we have already understood how the learning cycle works, this comparison becomes much clearer, because this is not just a technical difference, it's a completely different way of building the systems. Now, let's look at the left side first, traditional programming. Here, the responsibility is entirely on the human. You analyze the problem, you break it down, and you write explicit rules for every possible situation. So, the flow is very direct. You give the computer an input and a set of rules, and it produces the output. For example, think about something like calculating discounts. You might write, if customer is premium, give 20%. If purchase exceeds a certain amount, add another discount. Everything is predefined. The system does exactly what you told it to do. Nothing more, nothing less. So in this setup, the human does the thinking and the machine does the execution. Now look at the right side, machine learning. Here the process flips. You don't start with rules, you start with examples. So instead of telling the system, here's how you solve the problem, you show it, here are many solved examples, figure out the pattern. And let's take a more complex case, fraud detection in transactions. In traditional programming, you would try to write rules like, if transaction amount is unusually high, flag it. If location is unfamiliar, flag it. But fraud patterns constantly evolve. Attackers adapt and rules quickly become outdated. In machine learning, you approach it differently. You provide historical transactions labeled as fraud or not fraud. And now the system learns patterns such as unusual combinations of behavior or subtle timing patterns or deviations from a user's normal activity. Patterns that are too complex to manually define. So now, instead of executing rules, the system is discovering them. And that changes your role as a human. You are no longer writing step by step logic, you are curating data, defining what success looks like, and you are evaluating the outputs. You guide the learning process, you don't hardcode intelligence. And this shift from writing rules to providing examples is what made it possible to solve problems like image recognition, natural language understanding, and recommendation systems. Because problems where rules are either too complex or simply impossible to write explicitly. After understanding the differences, let's go one layer deeper now. Because the real shift is how machines actually see the world. Look at this side first. Traditional programming, rules, machine, and output. Everything depends on the rules. If the rule exists, the system works. If the rule doesn't exist, the system fails. And now compare that with machine learning. Data, machine, output. That one change, replacing rules with data, is what unlocks everything. Because now the system is not executing logic, it is extracting the patterns. And this brings us to the first key idea, statistical recognition. Machine learning doesn't understand in a human sense. It recognizes patterns based on probability. For example, in language, it does not know what a sentence means. It knows this sequence of words is likely to follow that sequence. And at scale, this becomes incredibly powerful because with enough data, pattern recognition can outperform human intuition in specific tasks. And now, this second idea, data processing evolution. Different types of data require different levels of learning. Traditional machine learning works well with structured data, things like tables, numbers, transaction records. For example, fraud detection, you have clear fields, amount, location, and time. But when you move to unstructured data like images, audio, or language, things become much more complex. And this is where deep learning becomes essential because it can automatically extract features from raw data. So the evolution is not random. It's driven by the type and complexity of data. And now let's ground this with something real. Think about a spam filter. It has seen millions of emails, some labeled as spam, some not. And over time, it learns patterns like phrasing, the structure, and subtle variations. So, when a completely new email arrives, even if the system has never seen that exact message before, it can still classify it correctly. And that's the power of pattern learning, generalizing beyond seen examples. But there is an important limitation, and this is where many misunderstand AI. The system has predictive limits. AI is very good at predicting what is likely, but it does not understand why in a casual sense. For example, it might learn that dark clouds refers to rain, but it doesn't understand atmospheric physics. It doesn't reason about cause and effect, and it's operating on correlation and not true understanding. And this distinction matters because it explains both why AI is so powerful and why it can still make mistakes. So, if you connect everything on this slide, the machine learning is fundamentally about replacing rules with data, recognizing patterns at scale, improving through exposure, but always within the limits of probability, and it does not perform true reasoning. Now, let's take everything we have discussed so far and put it into one concrete example because this is where the difference really becomes obvious. Let's start with a problem. Predict whether a student will be a topper. Okay, let's first solve this using the traditional programming. In a rule-based approach, you start with writing conditions. For example, if marks are above 90, it results in topper. If marks are above 75 and attendance is high, he'll become a likely topper. If homework completion is above a threshold, it results in a topper. If extra classes attended, add bonus. You keep adding rules, trying to cover every possible scenario. But here is the issue. Real students don't behave in clean, predictable ways. You might have a student with average marks but extreme consistency, a student with high marks but poor attendance, and someone who improves drastically over time. Now, what do? You add more rules, and more rules, At some point, the system becomes complex and hard to maintain, but the system will still be incomplete because no matter how many rules you write, there will always be edge cases you did not anticipate. Now, let's solve the same problem using machine learning. Instead of writing rules, you start with data. You feed the system thousands of student records. Each record includes things like marks, attendance, homework, and performance trends. Now, the system looks at all of this together, not one rule at a time, but all variables simultaneously. And it starts finding patterns. For example, it might discover something like students who are consistent over time with moderate scores and high attendance often outperform students who score high ones but are inconsistent. Now, notice something important. No human explicitly wrote that rule. The system discovered it. And once it learns these patterns, it can apply them to new students, predicting outcomes with much higher flexibility. Also, when new patterns emerge, you don't rewrite rules. You just provide more data and the system adapts. So, both approaches solve the same problem, but the way they get there is completely different. Rule based systems try to define intelligence upfront, whereas machine learning systems extract intelligence from the data. Now, let's ground all of this in a real system that you have actually used, your email spam filter. There are three important things happening here. Let's take them one by one. First, no explicit rules were written. Nobody programmed something like if an email says lottery, mark it as spam, because that approach breaks immediately. Spam keeps changing. The wording evolves, the structure changes, and new tricks continuously appear. So, instead of writing rules, the system was trained on examples. Second, it catches spam nobody has seen before. And this is where the machine learning becomes powerful. The system is not memorizing emails, it's learning patterns. For example, it learns combinations like how certain phrases appear together, how suspicious emails are structured, how behavior differs from normal emails. So, when a completely new spam email appears, even if no human has seen it before, the system can still detect it. Not because it recognizes the exact message, but because it recognizes the pattern behind it. And that is a fundamental shift from memorizing to generalizing. Third, it is trained on massive amounts of labeled data. This process doesn't work with a small dataset. The system learns from millions of emails that humans have already classified as spam or not spam. And that scale is what allows it to pick up subtle differences. For example, a marketing email versus an actual spam, a real notification versus a phishing attempt. These are very close in appearance, but across millions of examples, the patterns become clearer. So, if you step back, this entire system works because of three things: no hard-coded rules, ability to generalize to new cases, learning from massive labeled data. And when you open your inbox and spam is already filtered out, you are seeing all three of these steps working together. Now,